Companies around the world have been trying to bring advancements to AI for decades. In the last 4 years, they've made significant progress in processing power. This is a study done by IBM and the University of California back in 2017. It was funded by DARPA. The study concluded that the von Neumann architecture, which is defined by strict and hierarchical separation of memory and processor, is becoming increasingly unsuitable for cognitive applications which require massive parallel processing of highly interdependent data. We propose a significantly different architecture characterized by a large number of highly interconnected simple processors intertwined with very large amounts of low latency memory. In the von Neumann architecture, keeping the processor and memory separate causes too many inefficiencies when it comes to AI processing. And on top of that, Moore's law, which states that roughly every 2 years the number of transistors on a microchip will double, is coming to an end. It's really technical, but essentially silicon atoms are only 0.2 nanometers wide, and we have transistors have a gate length of 2 nanometers, and if they go any smaller, it would affect the flow of electrons. So we can no longer rely on Moore's law to consistently increase processing power every 2 years. GPUs are able to process data much faster than CPUs, so most companies have been using GPU clusters like this one for AI processing, but the data has to go from the silicon of one GPU through the wires and onto the next GPU, which is slow and highly inefficient. This led to the creation of the Wafer scale engine, which is the largest chip ever built. The Wafer scale engine is a chip made out of an entire wafer of silicon, when normally one wafer is used to cut out dozens of processors. This was created by a company called Cerebras Systems, and they are currently on their second iteration of processors, which they named the Wafer Scale Engine 2. Compared to the largest GPU, the Wafer Scale Engine 2 is 56 times larger, has 123 times more compute cores, and 1,000 times more high-performance on-chip memory. It contains 2.6 trillion transistors, 850,000 AI cores, 40 gigabytes of on-chip memory, is able to process 20 petabytes of information a second. That is 20,000 terabytes a second. Each wafer contains 84 processors and all are connected to each other on the silicon wafer, which eliminates the communication slowdown and inefficiencies of connecting hundreds of small devices via wires and cables. The result is faster, more efficient execution for computing work at a fraction of the power draw for traditional GPU clusters. According to the tests, the data transfer speed on the wafer is equivalent to that of 2,100,000 gigabyte Ethernet wires. Each processor is also designed with sparsity in mind, which means that each processor will filter out unnecessary computations when communicating with their neighbors, which is different than traditional GPU clusters. This saves power and significantly improves performance when computing. The idea of using an entire silicon wafer for one chip is nothing new. This has been pursued since the 1980s. Creating the Wafer scale engine took 173 engineers and $112 million, and Cerebras had to overcome 5 major technical challenges to make this a reality. The Wafer scale engine 2 is the future of AI processing. It is far more capable than any GPU can or will be with our current manufacturing practices, and if these processors are stacked, they have the capability of being far more brain-like than the von Neumann architecture allows.